Okay, then, so thank you. Sorry for the delays. And so welcome everyone to this first edition in 2025 of the LATAM BISH Bash. So for those of you joining us for the first time, this is kind of a series of meetings and networking events that try to contact researchers, engineers, students, and companies working on everything related to music, speech, acoustics, audio, and everything in between. This time we will have a very special program consisting of 3 talks of works that were presented last year during our first Latin American workshop on MIR. And so just to say what the LATAM BISH Bash is, so is basically an informal networking meetup to bring together the Latin American audio, speech, and acoustics and music research community. So all of this is thanks to some sponsoring from the IEEE Signal Processing Society. And so we have a nice organization team that has been able to work quite nicely, including both Magdalena Fuentes, Andres Ferraro, and myself, and some lovely student organizers who do actually most of the work. In any case, so we have a very nice program today. So we have these 3 talks by Breno Matos, Felipe Marra, and Lucas Somacal. We will start with the first talk by Breno Matos. I've heard this before, initial results on TikTok's impact on re-popularization of songs. And Breno is a data scientist at Kunumi working with LLMs. He holds a bachelor's degree and a master's degree in computer science from the Federal University of Minas Gerais, and is a recipient of the Google Latin America Research Award. With a background in computer science and experience from research labs to tech companies, his research spans natural language processing, misinformation detection, and online phenomenon analysis. And he will present his latest work where he explores the role of TikTok in repopularization of older songs. So, Breno, the stage is yours.
Okay, let me share the screen. Okay. Can you guys see my screen?
Yes.
Okay, so let me just fix my speaker notes here and I'll start in a minute. Okay. Right. So, hi everyone, I'm Breno, and today I'll be presenting, as Carlos said, I've heard this before, initial results on TikTok's impact on the repopularization of songs. So this work was presented at LAMIR by a team, and it was work from a team from UFMG and Kunumi, which is the company I work at right now. And so basically me, Renan Francisco, and I did this work as a coursework assignment during our master's. And we were advised by Professor Flavio, who leads the Uncertainty in Artificial Intelligence lab at UFMG as well. And here's a picture of us presenting the work at LAMIR. Very, very fun. So our main motivation is that TikTok has become one of the major players in how people discover and consume music online, which is, if you've used TikTok before, is something that you might have seen for yourself, because audio, not only songs, but audio in general goes viral. And what's interesting is that it's how old songs, sometimes even decades old, can suddenly go viral again. And this is something that's specific for TikTok, but its short form video format means that sometimes only snippets of a song, like 15 to 30 seconds, go viral, and which is a different virality pattern when compared to other more traditional social media platforms. So we wanted to understand, basically, is TikTok driving this song resurgence? And if so, can we measure that effect? And okay, so we are driven by 2 research questions. So first, does TikTok influence web search popularity? And then how do TikTok trends transfer to broad virality on the web as captured by Google searches? and I'll go into detail on how each of these work. So first, we needed to construct to build our data set, which is available upon request. And actually, this was something interesting. We had researchers already asking for the data for this, and I don't know, maybe we'll get a few citations further on, but that's besides the point. Okay, so then we use Talkboard, which used to track TikTok song popularity. So all of the data we gathered covers until 2022, and then we matched this song popularity data with Google Trends data, and also the songs had to be released pre-TikTok. This, of course, is to ensure that TikTok has had some impact on making the song go viral, because again, if the song goes viral after TikTok exists, then we can't really pinpoint TikTok's effect on making this go viral. Okay, so, and also the song had to have a clear viral moment, so a peak in interest. So after filtering and validating, basically making sure that all the audio files that we were working here with here were songs and not only audio memes, because again, this is something that's specific to TikTok. Sometimes the meme itself is actually the audio. So everyone records a video on top of that audio, and the audio stays the same, but and everyone puts their own spin to their videos, but the meme itself is arguably the audio only. And afterwards, we had a final selection of 30 songs that fitted our purpose here. And instead of going for quantity, which again was possible because we had information of many other songs, we wanted a high quality, well-aligned data set of initially 30 songs that we were able to compare trends across platforms. So TikTok and Google Trends. And we use Google Trends here as a lens to the web in general, right? So this is a screenshot of Talk Chart, actually. So the thing is, Talkboard was deactivated, I think, last year. So it's not available anymore. And I think that happened because the makers of the website wanted to make some money, and then they made this new version, Talk Chart, that's paid. But it contains basically the same information, but using a better website. But I'm only showing this because I wanted to give an idea of how Talkboard used to work. I couldn't find a screenshot from Talkboard itself, but basically they kept track of trends, audio trends across TikTok, and you can now filter by country, dates, etc. And also they kept individual curves for interest or plays for each audio, which in this case we have two examples here. So okay, on the left here we have an example of the pattern that we wanted to observe. Basically, we initially have a surge in interest on Talkboard, which is a proxy for TikTok. And when I say interest on Talkboard or TikTok interest, you can understand these as interchangeable. But basically, we have a peak of interest on TikTok, and afterwards we see an increase of interest in observed on Google Trends. And on the right, we show a complementary cumulative distribution function of the popularity of Talkboard songs so far. And the y-axis on this plot captures the fraction of songs with popularity higher than the x-axis. And so from the figure, what I want you guys to understand is that Talkboard only monitored highly popular content because the scale of plot is tens of billions of plays. So to investigate our research questions, we used two main tools. So first, the Granger causality test to understand basically, does TikTok influence web search popularity? And basically what Granger causality does is checks if TikTok activity can predict Google Trends activity or interest. And second, we used the base diffusion model, which is a classic framework to model how innovation spreads, looking at who adopts songs early and who imitates others. And in this case, we used a high p-value, unfortunately. But again, these are initial results, so 0.1. And overall, what the Granger causality model does is it tests whether one time series can predict another. Basically, X Granger causes Y if past values of X improve prediction of Y, and this is used to understand directional relationships in time-based data, which is exactly what we're trying to do here. And the Granger test found that in about a third of cases, basically 10 songs, TikTok activity statistically predicts a rising web search, as seen in these other two examples here. And again, this is similar to the first example I showed. Basically, we have a surge of talkboard interest. This after some time fades, but it has a lasting effect on the Google Trends data or interest. So TikTok isn't always the cause for this, but when it is, we have a somewhat clear signal. And these are some examples of that. We also have more examples on the paper as well. Okay, so for our second research question, we used the base model, as I mentioned. And basically, this model is primarily used to understand how new ideas or products are spread over time. And they have two adopter types, innovators and imitators. And these end up being parameters for the base models that we propose. So as I mentioned, we only had good causality for 10 songs, so a third of our initial data set. And for these 10 songs, we fit the base model on TikTok and Google Trends data. And for these cases, the results were closely aligned, meaning that the way a song spreads on TikTok tends to mirror how it spreads in Google search. Sorry, the opposite. And that's an evidence of cross-platform influence. So basically, we can see that TikTok can have an impact on how the song becomes viral again and how this spreads to broader web activity. Okay, so these are a few examples of how this works. You can see that the cumulative popularity for both on these three examples here are very similar. And on the top left here, we have a linear regression between the parameters for each base model. Basically, we show talkboard parameters and Google Trend parameters for each, and you can see that we can achieve a fairly good linear regression, meaning that the parameters for both are similar, and this showcases what I mentioned, that basically we see similar patterns for both TikTok and broader search patterns, as evident as using Google Trends as a proxy. So what did we find? First, that TikTok has some impact, or it can bring old songs back to the spotlight. And second, it's a reliable predictor in a few cases. And third, that the shape of a song's virality, basically how fast and wide it spreads, is often shared across TikTok and the web. And this alignment suggests that a song's momentum on TikTok can lead to a sustained interest in search activity elsewhere, which is, we argue, is an evidence of cultural spillover. And okay, so of course, this work is very limited. These are initial results on this effect that we wanted to measure. So first, we are only limited to 30 songs. Again, we have information on many other audio files or even songs as well, but for the purposes of these experiments, we only had 30 songs. The data only goes so far as 2022, as I mentioned, because Talkboard doesn't exist anymore. And also our data set doesn't include who is listening and how they interact with that. So for example, we don't have any social media signals such as commenting, liking, reposting, sharing, etc., which could be also good indicators of how these songs go viral. So as next steps, we believe that first we can study the economic impact. So for example, how much a viral TikTok with a song boosts Spotify playlists. And also we could delve into demographic analysis, such as which age groups or even country-specific data, which is also now available on the new Talkboard or Talkchart. And also I wanted to mention a somewhat abandoned track that we tried while doing this paper, which was we wanted to use Spotify playlists as a proxy for popularity as well. So we crawled a few Spotify playlists, like the top 50, I think, like for each country, stuff like that. But we have that data, but we really didn't find anything interesting using that. But again, this might be a problem with how few data we had, or I don't know, something related to methodology, and of course can be improved. So in conclusion, this paper gives us a new lens to understand TikTok's power in reviving music. And in this case, we try to combine causality with virality modeling to understand basically that virality isn't random, and it can be somewhat tracked and even predicted. And we believe that this work opens new avenues and research directions in music and social media research, which regarding social media research is my background. I don't have a background in audio processing, so that's where the initial idea came from. And that's all. Thanks.
Nice. Thank you, Breno. We do have some time for questions. Do we have any questions? If no, I do. So I'll get started. One thing that I was thinking, I think that my understanding is that the motivation to use Google Trends, actually, I don't really understand the motivation, so this is the first part of my question. But my second question / comment is that usually when we see those viral contents, you see there's like a cascade. So they happen first in, I don't know, TikTok, and they get spread to other social media. So you see the same content in Instagram, and then after you see it in Facebook, and by the time it gets to Facebook, then you like it's a very long time after, and it's when your mom show you something that you have seen like 3 weeks ago or something. So I think my question is, why did you decide to go to Google Trends instead of going to somewhere that you could find this effect maybe more immediate? For example.
Okay, so first I think the Google Trends approach was the most, I guess, the most that combined a somewhat easy solution, but also a sound solution as well. And why is that? These days, people, I guess, people use I don't know, ChatGPT a lot more instead of searching for things on Google, but Google is still very much used. And we wanted we used Google Trends because we wanted to use these web searches as a proxy for popularity. Because, for example, these videos that you're mentioning that are now on Instagram or Facebook or whatever are also indexed, so they technically would show up when you search for something. But I completely agree with you. The best approach would be to get this data from social media platforms themselves. But I think this involves somewhat hard challenges, because I mean, crawling these social networks is not something, for some of them, it's not trivial. For example, Instagram doesn't really have an API we could use, there are only workarounds to crawling the web data, and I've worked with this before as well. But also there's a problem that I think is that matching the video. So making sure that one video is the same as the other one. And I don't have a background in, I don't know, image processing or video processing. I think that's possible to do, but I'm not sure how. And basically, how could we start? Like, because for example, the TikTok search works pretty well. Like, you can really find what you want. But for example, the Instagram search, in my opinion, sucks. Like, if I search for something, I mean, I don't really find I can't really find what I want. And then what's our starting point, right? To find these videos, match these videos, and then, but I mean, if we could do that, I agree. It's like very, very, very interesting.
Nice, thank you. Do we have any other questions? Are we good on time, actually? Oh, there's a question. Okay, so Rodrigo is asking a question. My chat is not opening. Can someone read the question, please?
Yeah. Well, can you see the question, Breno? Or
Yeah. So it's quite clear that when a song goes viral in TikTok, there's a high chance that Google searches will increase after some time. But why repopularization and not popularization? Because we wanted to focus on what we call older songs. So that's why we have a data cutoff for songs that were released pre-TikTok. So just an example that maybe someone here saw online. The song Dreams by Fleetwood Mac was a good example of this. Like, it's a song from the 80s, I think. And then we had basically a TikTok trend on this. And the data cutoff is very, very important in our case, because I don't know if this happens worldwide, but at least in Brazil, sometimes artists release a song with the intention of like releasing also a TikTok trend, like a dance for people to interact with and make the song go viral. So that's why we call it repopularization, because these songs are pre-TikTok.
Nice. Okay, thank you for the answers. Thank you for the presentation, Breno. It was very nice. I think we can move forward because of time. We have 2 more presentations. Carlos, do you have Felipe's
Yep. Yeah, so I think Felipe, you can start sharing your screen.
Okay.
And so then Felipe Marra is a master student in deep learning at the Federal University of Viçosa, and he's a visiting researcher and member of the Mosaic Group at the Federal University of Minas Gerais. Currently, he's interested in multimodal architectures comprehending video and audio. So Felipe, the floor is yours.
Okay, so can you see the presentation?
Yes.
Yes.
Okay, so I'm going to present our paper that got accepted at the LAMIR 2024 workshop, entitled Long-Form Text-to-Music Generation with Adaptive Prompts, a case of study in tabletop role-playing game soundtracks, or just Babel Bardo, as it is the name of the model we present in the paper and how we call it internally. My name is Felipe Marra, and this is Lucas, my advisor and the other author of the paper. We are both members of the Mosaic Group, an emerging group in computational creativity at the Federal University of Minas Gerais, with professors from the CS department and the School of Music. The works I'm going to present today are related to music recommendation or generation for tabletop RPGs. But why music for tabletop RPGs? A system that aims to recommend or generate music for such scenario will need to adapt to the player's improvisations, and the unpredictable consequences of dice rolls in real time. And since RPG campaigns usually last for many, many hours, this is naturally a long-form recommendation or generation problem, which ideally implies in some huge challenges, like the system having to remember what it recommended or generated long, long before in order to create musical themes and that kind of stuff. I'm going to quickly talk about the previous Bardo systems. We went from the player speeches to music recommendation or symbolic music. Babel Bardo, the one we presented at LAMIR, that was from the player speeches to audio generation, music in raw audio, right? And our future work, we are planning to go from video to music in raw audio. So the first Bardo, it took the player's speeches, transcribed it, and used an story emotion classifier to get the emotion in the story and an algorithm to recommend a song that matches such an emotion, and started playing that song. And you might just keep the same song if there wasn't an emotional change in the story, or when it detects a strong enough signal of a new emotion, it might just adapt to continue matching the emotion in the story. A follow-up work was Bardo Composer, which starts with the same idea, taking the player's speech's transcription, classifying it to get an emotion. And here comes a little bit scarier box where they use a language model to generate the symbolic music and a music emotion classifier to classify the emotion of the music that was being generated, along with a search to steer the generation at inference time to match the emotion in the story. And we might just call this a symbolic music generator, and this unfolds over time. Then the work we presented at LAMIR is the latest Bardo version. We used LLMs and text-to-music models, so text as interface between every step. And since we took campaigns from YouTube, they were already edited with music, so we can evaluate on music chosen by humans. And we think that this might be a nice framework for evaluating these text-to-music models, because they are usually only evaluated on like at most 30 seconds of audio. So we start taking 30 seconds of the player's speeches, transcribing it, using a large language model to generate a music description that we use to feed a text-to-music model. And we get our music, and this unfolds over time. And here's a quick demo. This is a campaign on YouTube that we replaced the original music by the one generated by our system.
There is no audio. Felipe, Felipe, can you hear me?
Okay, so we have 4 versions of the system. The one from the demo will be the 4th one. The first one, we just call it baseline because we skip the LLM altogether and just feed the text-to-music model with the player speeches. We have the emotion version that kind of imitates Bardo Composer. We use the LLM as a story emotion classifier. And we
Felipe,
use the same emotions that were used in the original Bardo composer. We feed the text to music model with a prompt like generate a music with the following emotion, and we just use the LLM output as a parameter. We also have the description version, which generates a new description every 30 seconds, and the description continuation version, which we prompt the LLM to try to identify if the current 30 seconds are in the same context or in the same scene as the previous 30 seconds. If so, it will not generate a new description, and the text to music model will just continue condition just on the previous audio. Otherwise, it will generate a new description to match the new scene. So we evaluated the system in 2 tabletop RPGs, campaigns that you can find on YouTube. Call of the Wild in American English was the one on the demo, and O Segredo na Ilha in Brazilian Portuguese, that have a original soundtrack they created from scratch. And so to evaluate audio quality, we use the FAD metric calculated with the BISH model. We use 32 hours of high quality soundtracks as our ground truth, and those do not include the ones edited into the YouTube videos, because we also get the value for the human music to have like what could possibly be the best value. So we generate 30 minutes of audio starting at a random point for each episode of the RPG campaigns. We get the FAD for each episode and average them. So the FAD results for the human music, we got 3 for Call of the Wild and 4.18 for O Segredo na Ilha. And for our Babel Bardo versions, the description continuation one got the best result. For story alignment, we use KLD with the past model, and we fine-tuned it on the MTG Jamendo dataset to get a better sense of instruments, genres, and mood. And whenever I refer to KLD, you have to imagine that what we actually did was calculate the KLD for each of the independent classes the classifier returns, and we sum the results for every 10 seconds, because the past model is limited to 10 seconds. So as a concrete example, here is the output for the past model fine-tuned on the MTG Jamendo dataset for the Prison Song from System of a Down. So you can see that for metal, you have a high probability, also for bass, drums, and electric guitar. So we calculate the KLD for each of these independent distributions, and we sum all of it every 10 seconds. So this mean KL divergency was calculated by, again, generating 30 minutes of audio starting at a random point for each of the episodes of the RPG campaigns. We take the KLD of the generated music against the human ground truth, right? The music that was edited into those videos. We do this in 10 seconds windows and take the mean. So the results show that the motion version have the best KL divergency result. So for Call of the Wild and O Segredo na Ilha. We also wanted to evaluate what we call transition KLD, because since we change we can change the music description every 30 seconds, the model will have to adapt the previous audio to fit in the new musical description. So every 30 seconds, we have these transition points where the model have to adapt. So we take the 10 seconds before the transition point and the 10 seconds after, and we take the KLD between those two. So if the KLD value is low, then this is probably a smoother transition than if it was a high value. So the results show again that the emotion version won in both campaigns. And from this, we can conclude that detailed music descriptions help improve audio quality because the description continuation version won the FAD. So it is a version that generates more complex prompts and change prompts frequently. And it had a better FAD. So, and the emotion it might be a strong signal for generating soundtracks for RPGs because the emotion version that like just changes one word from one prompt to another, that is just one of those four emotions, was the better in story alignment. Also, consistency across consecutive descriptions is important for smoother transitions, as the emotion version won again, and it just changes one word from one prompt to another. And the future work we are doing at the Mosaic group right now, we want to create a Bardo version that really works in real time, because the current versions, they might work in real time if you have like infinite computational power, but don't in practice. And we want, and my master's thesis will work around this, what we're calling visual bardo, which where we want to go from video to music in raw audio. So demo paper and code are available at this link, or this QR code that points towards this link. And that's it.
Felipe, I think when you share the screen, I'm not sure if you share the audio also. So would you mind showing us the demo again? You just need to like unshare a screen, reshare it with the audio, and then replay the video you showed in the middle of your presentation.
Oh, there is a share sound checkbox here. Okay. See. Just a second. I never presented in Zoom, guys. I'm kind of. So is this? Yeah. Okay. Is it still the same presentation?
Yeah, you're actually on the same slide, yeah.
Okay. So let me try to play it again. I think I skipped it. No, I didn't. I skipped it. Come on. Okay. What? Where is it?
I think it's
Okay.
just that. Yeah.
I found it. Okay. Okay. Okay, sorry. So are you listening now?
Rolling this shit up here. Rolling up the oh, shoot. His ready to action was, if he's harmed, he's gonna fucking start trying to kill you. But he's trying to be reasonable and quiet here. So, what happens? Ego comes up, like casts this spell on this piece of wood, and he's like, fine. He's like, and he rages out, and now he's going to try and fight you guys. As he goes, and he like.
Yeah.
Thanks. Really cool demo, by the way.
Yeah, there are a lot of other results in the link I put it at the end. The site is not the best one.
Maybe you want to send here in the chat the website so people can access the link and people can access. I think because of time, I'm not sure if we will be able to have questions for this. Maybe we should move to the last presentation. And then if people want to stay a bit more, we can stay a bit more. But for the sake of time, let's move on to the next presentation, if that is fine. But thank you. It was very interesting.
Thanks.
Okay, so Lucas, do you want to share your screen while I introduce you?
Yeah.
I will share Lucas' screen.
Okay, yeah.
Okay. Yeah, maybe.
Okay, then great. So for our final presentation today, we have Lucas Somacal. So he's a data scientist at Satoshi Foundation and Quantit, a startup specializing in AI. He obtained a master's degree in computer science at the University of Buenos Aires, and his master's thesis in music style transfer was presented at LAMIR 2024. And so his research interests cover optimization and machine learning problems and their ethical implications. He's also a musician and currently a student of singing and orchestral conduction at the Universidad Nacional de las Artes de Argentina. Then the stage is yours, Lucas.
Yeah, perfect. Thank you for the other presentations and your presentation. What we were to discuss is why or how symbolic music, how we can do site transfer of symbolic music via latent space transformations, that is with the latent space of a variation autoencoder. And we did a model and we present new evaluation methods for this task that is not very famous. So next, please. Well, what we did was, I want to present is that two various autoencoders that transform a symbolic musical fragment from one style to another. That is, for example, from rock to pop. We want to change the style of the fragment, achieving good results in 3 points. That they are resemblance to the target style, musicality, and identity preservation. Yeah. So the goal is to change the style of an existing piece of music in symbolic format to mimic a specific music style. And well, as I said before, to present new evaluation methods. Well, the next one, please. Yes, I start with the introduction. So yes, thank you. There are not many works on symbolic style transfer, but there are a few ones. For example, using generative adversarial networks, that is a model that can transfer from one specific source style to one specific target style. And generative models that do continuations for an input musical fragment in a specific style. For the evaluation methods, we have a subjective listening tests with surveys, for example, comparison of the and they do comparison of the distribution of features to assess musicality for one side, and from the other hand, they do a comparison of prediction of style classifiers. So the next one, please. Thank you. What we did, or we propose, is to do multi-style transfer. So with the single model, that is one single model to do transfer style from different, not only one style. We did it with a latent space vector arithmetic, and we introduced a parameter alpha between 0 and 1 to adjust this transformation level. On the side of the evaluation methods, well, we present these 3 points that are how to measure how close are we to the target musical style, if the generated fragment is musical, and if the generated fragment still resembles to the input. Yes, I don't want to change everything of the song. I want to preserve some characteristic of the input. So yes, the next one, please. The methods we used was, first of all, the data sets. We used the LAMIR dataset for pre-train a model that was one of the models that we keep to compare with the second model, that is the fine-tuned with kernel scores with 4 styles, 4 specific styles that were Bach's chorals, Frescobaldi's canzoni. Frescobaldi was a composer of the Baroque era, Mozart piano sonatas, and ragtimes, summarizing 2,000 fragments. And we keep a validation set of 10% of the kernel scores of these 4 styles. So to represent the music, we used matrices of zeros and ones of 64 to 4 times 89 columns with semiquavers. Yeah, they're representing 64 time units of semiquavers of 4 bars of 4 quarter notes. So we have totalizing 4 bars in total. We adapt a variational autoencoder presented by Guo in 2020 with an encoder, a latent space of 96 dimensions, and a decoder similar to the encoder with a few more internal layers. Well, so as I said, we trained 2 models. One we called pre-fine-tuning based on the LAMIR dataset, and one is the fine-tuning of kernel scores. Well, to modeling the musical style, we present two things. One is the melody approach, that we count for each style the first interval and which is the next interval after the first interval. That is, if I have, for example, a minor third for the first interval, which is the probability of that the next one was I don't know, a minor third as well. So we count how many intervals are the next of the others. So we can see that from the distribution of these pairs of intervals of the different styles are different. So we can characterize a style by the melody distributions of the note intervals. And we can see here in the left, for example, the Bach, the chorals, the Bach's chorals distributions, and in the right side, the ragtimes distributions. So you can see that the difference of these distributions. This was based on a paper of 2013, but it's not very famous, that paper. But it's very interesting to see how is the difference between the two distributions. So based on this, we adapted to 4 semi-quavers pattern bigrams. That is how different can be 4 semi-quavers. For example, the ta 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 ta, for example, which is the next pattern. So and we see the same thing, that each style has different distributions. Yes, right. Next one, please. So to do the style transfer process, we trained this variation autoencoder, and we encode the fragment, the musical fragment, and we add the characteristic vector of the style of the new style, and we subtract the characteristic vector of the original style, which is the characteristic vector is mainly the average of the vectors of the latent space in the latent space of the style. So, for example, if I want to transfer a Bach's choral to a ragtime, I compute the characteristic vector of the ragtime, I compute the characteristic vector of the Bach's choral, and I add to my single fragment the characteristic vector of the ragtimes. I subtract the characteristic vector of the chorals, and I decode this result. This is measured. It is quantified by the parameter alpha that I said, between 0 and 1, and that how many or how strong is the transformation, right? So the next one, please. To evaluate these results, we present, first of all, if the generated fragment belongs to the target style. So the next one, please. To do that, we affirm that a transformation is successful if the generated fragment is closer to the target style than the original fragment. That is, we measure the distance between a fragment and a style with optimal transport. In particular, we measure distance. We use to a distance method the optimal transport, and for each pair of source target style, we calculate the percentage of generated fragments that became closer to the target style. So in the next figure, we can see how with the in this figure we can see for different values of alpha how many are the successful transformations for each pair of styles. So we measure an average of these transformations, and we can see that if the alpha is greater, the transformation will be resemblance will be more closer to the target style that if the alpha is less is yes. For example, in this case, if alpha is 1, is better in this sense to the alpha lower, the lower alpha. So in the next slide, we can see the second point, that is if the generated fragment remains musical. To measure musicality, we call like a new style measured by we call the universal style, that is like an average of all of styles in the data set. And for each original fragment, we generate 20 permutations by reordering the nodes in time. So we suppose that these permutations, these random permutations, are less musical than the original permutation. So what we want to measure is that if the new generated fragment is closer to the original, the universal style distribution than these random permutations. Yeah. So in the next slide, we can see how with lower values of alpha, we have that it remains more musical, but if we transform a lot the fragment, this musicality goes down. But these are box plots, so the majority, a great part of the genetic fragments remains musical. We have only more dispersion on the results. So the next slide, please. Yeah. Well, and the third point, the final point, is that if the generated fragment is similar to the original, and we suppose that a generated fragment retains characteristics of the original fragment, the higher it appears in a similarity ranking. A similarity ranking measured by like a competition between the original fragment against the set composed of M of the generated fragment and all of the other fragments of the original style. That is, if I want to transform a Bach's choral, I compare the Bach's choral, the new Bach's choral, changed Bach's choral, and all of the Bach's chorals of the original style of the style, and the original Bach's chorals. So we said that two fragments similarity is the inverse of how many semitones the notes differ between one fragment and the other for each time instant. So we finally do a score bounded by 0 and 1 with this position in the ranking, right? So the next slide, please. So finally, we measure this similarity, and we found that, again, that when the alpha goes to 1, the similarity reduces, but if the alpha is low, the similarity, we keep similarity with the original side. So the next one, we can hear how these results are. First of all, we want to hear the original fragment. Here we can see for example, to ragtime. Yes, that one with alpha equal to 0.1. Yep, please. You can see that it's very similar, but it changes a little bit. So in this one, please. So it changes a little bit more, but you can see the resemblance of the original side. And yes, in the next one. The transformation was too high, so the result was not as expected, because you go too far. So I think it's to the other styles are similar, but to with different directions, right? So yeah, the next, we can go to the next slide. Yeah, that's very similar, but yeah, I think I haven't not. I don't want to keep a lot of time with that, but yes, as conclusions, we have that our models managed to generate new fragments that remained musical, kept the identity of the original fragment, and are closer to the target style. But this happened with certain values of alpha, principally between 0.1 and 0.5. We have to that a greater alpha implies more style approach but less musicality, and that the model trained on a general music dataset was successful even on the distinct set of evaluation styles. And we observed that the performance between specific source target style pairs is varied. This is not presented here, but yes, different pairs of source target style. Its behavior is a little bit different, but yes, it's not in the general are okay. So in the next one, please. Well, in particular, between Mozart and ragtime, the model struck, contrary to the original expectation that styles with similar complexity will yield better results. So as future work, we want to validate the metrics with the listener service and compare with previous work. And we want to do works with LLMs, and yeah, we want to compare as well the site-specific with general approach, like the LLMs, as I said. And well, this is the presentation, so you can go to the next slide. Thank you. And well, if you have any question or we have time, I don't know.
So thank you for the nice presentation. So I think we might have a couple minutes for questions. We are a little bit over time, but I think that we would be happy if there are questions. If not, probably I can start with one. What do you think would happen? So something that I thought was quite interesting is the idea of just with doing arithmetic operations to move within a style. What do you think might be interesting if you were to go within the same style, but further into that style? Like, for example, going into Bach and make it even more Bach-ier.
Yeah, I played a little bit with that. Yes, the change. Yes, it will change maybe the melody, the rhythm maybe not, but principally the melody. But yeah. Yes, the melody maybe will be the more variation, yeah, will be in the melody. We can measure as well, or we can hear or produce the vector, the characteristic vector, for example, of the style, and there we have yes, like these patterns of same rhythm or a generic melody that I don't know, it's like, I don't know, Bach or not, I don't know, it's like, yeah, like I don't know, yes, maybe the melody is the more the more change factor.
Thanks. Are there any other questions?
I do have a question, but I want to stop the recording first.